Hello, my name is Okke Batelaan. I'm a professor at Flinders University in Adelaide, Australia. And it's a great pleasure to introduce and interview here Wolfgang Kinzelbach. Wolfgang is an emeritus professor of hydromechanics at the ETH Zürich. And we are here at the start of the International Association of Hydrogeology's World Groundwater Congress in Davos, Switzerland, on Sunday, 8 September 2024. So thank you, Wolfgang, for making the time available to do this interview as part of the series of History of Hydrology. And I'd like to have a discussion with you here about your career and what it has meant for you, and if you made friends and how it all went. A little bit of background of your career. Now, we're here in Switzerland, and I believe Switzerland is your second home country, but you were born in post-war Germany. And can you tell us a little bit more about your background and who and what inspired you in your youth?
Okay, thanks first of all for having me. Talking about my youth, I was born in a small town on the River Rhine in Germany, and my father was a bookbinder and later also a bookseller.
Okay.
And that, of course, is one thing I have from my youth, that is the love for books and the respect for craftsmanship.
Okay.
But I still have two little things from my father which may also have influenced a lot my later career.
Mm-hmm.
And one is the spoils of war he brought back from France. He was a soldier in France, and he always joked that it was his only travel abroad, and that was even paid by the state. And from that war he brought back a game of mahjong, a Chinese game of mahjong.
Okay.
And we played it with him as kids, and we looked at these characters, and I was very fascinated by the Chinese characters. And that made me later learn Chinese.
Okay.
So that's one thing.
Yes.
Another thing is he taught me how to bind books. And also, maybe once a year, he did with the children something which is called marbling of paper.
Yeah.
Maybe you've seen these colored papers with these intricate flow patterns,
Yeah.
like turbulance or the common vortex streets, right?
Yeah.
So you put the colors on water and then it floats, and then with a comb you turn it around and it visualizes the flow.
Yeah.
And flow visualization was later also something I loved very much, and I think it has to do with the marbling experience with my father.
Yeah.
So these are things I think childhood still influences a lot what one does later. And maybe there's one more thing from my hometown. It's on the River Rhine. We have all these oxbow lakes. We used to go with the kayak around these oxbow lakes, seeing the birds and the plants and the water. So I think water was also a strong impression from my childhood.
Yes. And so during your youth, you were already interacting with water clearly and made some big impressions on you. And so you went to high school in Mainz, I believe. Yeah.
In high school in my hometown.
Yeah.
For university, I went to Mainz first.
To university in Mainz, and you studied there physics, and later also in Munich, I believe, physics. What made you choose physics?
Yeah, maybe one reason was that I had an excellent teacher of maths and physics in high school, who really made me interested in that subject, and he did experiments with us and all these things. And that was another thing, and that was, I always thought, well, to get a mark on a German essay, that's something which somehow is a bit subjective and arbitrary. But in maths and physics, you're objective, you know what is true and what is false.
Yeah.
That's what I thought in those days. Maybe nowadays I think that was a wrong judgment. There's a lot of vanity and power play also in these natural sciences like maths and physics.
Yeah. Okay. And so physics was clearly your thing, huh? And in 1972, I think and after your physics degree, you started kind of your professional life. And I've heard you describe it as a random walk, your whole career. So that's an interesting thing. We might come back to that. And so maybe we can trace the first part of your career. The first parts were in the US and then later in Nigeria. Can you enlighten us a bit in what brought you to the US and what you did there and why you ended up?
I had a scholarship from the German Scholarship Foundation to study in Stanford, actually as a physicist at the Stanford Linear Accelerator Center. Mm-hmm. But in those days, I already got my doubts whether high energy physics was the thing for my life. Mm-hmm. You know, when I looked at my father, he did his work in the evening. He had a heap of books which he had finished. He knew what he had done. Yeah. And in theoretical high energy physics, I was filling paper after paper, throwing it in the waste paper basket in the evening. I did not see that concrete progress. Maybe the subject is and was very difficult. Yeah. So I wanted to do something more relevant to society. That was my wish in those days. Yeah. And then I took, in parallel to my work at the SLEC, a master course in environmental engineering.
Okay. Yeah.
And
in Stanford.
Yes, in Stanford. Yeah. I never regretted that change because that meant I wanted to leave physics and go into something which has to do with environment. The environmental movement was just coming up in those days. It was very new, and I wanted to go into that. And I must say I had also a very good teacher for that in Stanford. That was Perry McCarty. Mm-hmm. He gave wonderful lectures, and that convinced me this is a subject for me. Actually, before leaving physics, I met Carl Friedrich von Weizsäcker, you know, the German physicist. He was on a sabbatical in Stanford, and I phoned him and said, can I come and discuss with you what a physicist can contribute to environmental science? So he invited me to his hotel. Mm-hmm. I dressed up with tie and everything. Yeah. And he was sitting in bathing suit at the pool. So he said, yeah, it must have, I wish I would have a picture of that.
Yes.
So, we discussed, and he said, well, a very natural thing for a physicist would be energy and environment. How does energy interact with our natural environment? And, we were very fundamental, you know. Yeah. So in the end, you cannot beat Carnot, and in the end, the waste heat will be the limit to growth. Well, this was completely wrong, of course. Yeah. And now we know that you can do the influence of the climate with much less, that is CO2 or the gases which are relevant for absorbing CO2, for absorbing sunlight. And you can do it like a pseudo with much less effort. Mm-hmm. You can heat the planet. You don't need to wait for all that waste heat. So still, he brought me into contact with a professor in Karlsruhe Nuclear Research Center, where I could go for a PhD.
Okay. So that was your start of your PhD? But
I did not go directly from Stanford to Karlsruhe. Yeah. By the time I went there, this professor had already gone to another place. But I went after Karlsruhe to Nigeria. Yeah. And that is another thing from my childhood dream. I wanted to see the world. Okay. And how to do it? Well, you take the initiative and you go and teach. And in Nigeria, I was a math teacher. I was teaching math in a college close to Lake Chad. Nowadays, I could not go there because that is the region where Boko Haram, this extremist sect, is really killing people left, right, and center, especially people who teach, because Boko Haram means the book is bad. That means the book of teaching. They were against all the Western culture, Western teaching, and I would be dead by now if I would have stayed. Anyway, I had a very good time there. This was after the Biafra War. Things were going upward. Everybody was optimistic, and I had a very good time there. Yeah. And but after 2 years, I saw if I want to grow, I have to go and compete with my peers. Yeah. I was making the math exam for a country, for a province larger than my own country, Germany. Yeah. at the age of 23 or 24. And you would never get that task in Germany before you're 55.
Yes.
So this made me kind of independent, but I knew I have to have the competition with my peers to grow.
Yeah.
So that is why I went back then to take my PhD. And then I went to Karlsruhe, and as I told you, the Häfele, who was the guy recommended to me by Weizsäcker, he had gone to Jülich, and I still wanted to go to Karlsruhe, which was close to my hometown. And there was another professor, and he took me.
Yeah. And so the PhD, 1975, I think you started at the Nuclear Research Center. That was kind of your first water topic that you worked on? Or what, can you tell us a bit more about your PhD topic?
Yes, it has to do with water. It was the problem of waste heat, because we had all these planned and existing nuclear power stations along the River Rhine, and they have to dump about 2/3 of their generated heat as waste heat into the river. And that, of course, was heating the River Rhine. And so one had to make plans how to use that cooling capacity within the limits given by this 3 degrees temperature increase criterion.
Yeah.
And so I made a plan, I made an optimization of how to use that river within the environmentally bearable limits.
Yeah.
So it was always this thing of how can we still develop, but still on the other side keep to some criteria not to overstep limits. So this was the task, and I did a model of the River Rhine with all these heat put into it, different scenarios. Okay. It was a quite interesting task, and then it went forgotten.
Yeah.
Now, 30 years later, people came for my thesis. Why? Because now we really get a problem with global heating.
Yeah.
The temperatures in the rivers, even in groundwater, in lakes, are going up. So this whole problem of what should the limits be, how much can we use, this is becoming a problem again.
Yeah.
We had France last year, where some rivers were so warm that they had to switch off power stations.
Yeah.
And so it is a problem still today.
Yeah.
But research-wise, it was a problem where it was already at the peak. So after that, it went down. And I think you have to enter a subject when it is in the beginning. That happened to me later. I will tell you about that.
Okay. And so after your PhD, you worked for more than 2 years in Beijing for the Academia Sinica. And moving in 1979 to China sounds like quite an experience, an adventure. Can you tell us a bit more about what made you move to China and to work there, and how it was to work in China, and maybe you also learned Chinese before or after or during that time?
Yeah, I told you about my experience with Mahjong. So I learned Chinese actually as a hobby during my time in University of Mainz and Munich.
Yeah.
And in the end, I married a Chinese wife from Taiwan.
Yeah.
And after my PhD, we decided we would like to go and see what is happening in mainland China.
Yeah.
And I got this possibility through the Max Planck Society, first to visit with a delegation, and then after that to stay in an institute for 2 years. This was the Institute of Environmental Chemistry. Now it's called the Institute of Ecology and Environment of the Chinese Academy of Sciences.
Yeah.
And I spent 2 years there. Very interesting. I worked on water, of course. I worked on oxygen in rivers, BODDO modeling in rivers.
Yeah.
I worked on lakes, eutrophication, and this kind of work, applied work on actual environmental problems in China.
Yeah.
And so after 2 years, I went back then to Germany. Yeah, the 2 years, I must say, they were very interesting. It was a time in China when you had the mall of democracy. People started to speak out. I think in the public, in the visual side, it was much more free than nowadays.
Yeah.
Of course, the life was much more poor than it is now. Now you see these glitzy facades and everything looks like a big Western town.
Yeah.
But in those days, people were much poorer. But I think the relationships were much more interesting and better.
Yeah.
So less superficial. It was nice. I really enjoyed it.
Yeah. No, that I can imagine that was a big experience. And so in 1981, I think you returned to Germany, and you essentially, I think, commenced your groundwater scientific career. And most of us know you from that period. And it's interesting to hear what you all did before you actually turned to a groundwater hydrologist. And so it took you in Germany during, I think, 15 years along 3 universities, first Stuttgart, then Kassel, and then Heidelberg. Can you kind of tell us what, for you, the scientific highlights were in those years, and how you developed your groundwater scientific career?
Yeah, I told you it's quite important for a career at which point you enter the subject. And I went back to Stuttgart University, and then there was the problem of chlorinated hydrocarbons. Everybody had thought, I mean, these substances, they are wonderful, they are safe, they don't explode, you can clean clothes with it without this cleaning shop exploding once a year. So this was a nice new substance, but then it was found out that it pollutes groundwater. It's a very stable substance like dichloroethane, etc., perchloroethylene. And these substances, if they leak in the soil, they will end up in the groundwater. And our rule of thumb was with 1 liter of gasoline, you can spoil about, if you mix completely, 1 million of liters of water, drinking water. Yeah. And then with the corresponding limits for chlorinated hydrocarbon, you could spoil with 1 liter 100 million liters of groundwater. So the potential of pollution was very high, and actually in Germany they were found just by chance. People were worried that chlorination of water would produce chloroform, which is a carcinogenic substance, and they didn't find it. So chlorination did not cause chloroform, despite some organic substances being in the water. But they found a lot of these chlorinated hydrocarbon solvents. And that was the start of the research unit. I was in the first project in Germany, in a region around Mannheim, Heidelberg area. And we looked at how does it propagate in the ground, how can we do something against it. I was always more in the engineering side. What can we do? Just to know the world is bad, the world is going down, that was not enough. You want to do something to prevent it from going down the drain. So how can we remediate? So I spent a lot of time on remediation of chlorinated hydrocarbon, so spills. And I must say in the end, maybe in some cases we were successful with pump and treat. But pump and treat in some cases where a lot of this substance in phase has gone in the underground, it's the never-ending story. It goes for a long, long time. And so I think it was on the whole a frustrating experience that you can do so little. So I was more interested then in how can we prevent the pollution of groundwater by protection zone, by protection perimeters, by knowing the catchments of groundwater wells. So we did a lot of work of how to determine catchments, not only in the, let's say, deterministic way, but also not knowing too much about an aquifer in a more stochastic way. What should we protect to be sure that this well is safe? So this was the consequence out of this not being able to really remediate these substances. Nowadays, this whole remediation business, which I thought in those days would take off, it has gone down. Nowadays, they say controlled self-attenuation. It is a euphemism which says we cannot do anything, we just observe what is going on. Now, for some substances, it works. If you look at a oil spill, for example, it grows, and then all of a sudden it stops, and then becomes small again because the microbial activity in the underground will use the substrate together with the oxygen or some other electron acceptor and oxidate it away.
Yeah.
So it works for some, but it did not work for the chlorine hydrocarbon because that was a man-made substance. There were no organisms yet able to take some energy out of that substrate, and only under very highly anaerobic conditions there was degradation. And this was also researched in those days by colleagues of mine. Yeah, that was the chlorine hydrocarbons. That was mainly Stuttgart. And then still in Stuttgart, I went on with nitrate. That was the next wave of pollutant which came, nitrate in groundwater with the possible formation of nitrosamine in the body, cancerogenious again, and the blue babies and these kind of things. It was, I would say, intellectually interesting to see where does the nitrate come from. Mm-hmm. We had a case, very interesting case. You had asparagus fields, you had other agriculture, you had a forest, you had everything. Yeah. And in this place, all of a sudden, nitrate went up. Mm-hmm. So we were interdisciplinary group of people. I was the hydraulic guy. Yeah. There was also a soil mechanics guy from the Pluch. Mm-hmm. And there was a guy from chemistry. Mm-hmm. And we had all different ideas. Yeah. So as a hydrologist, I said, well, this well has suddenly more nitrate because there was a plume. They switched off the other well, and this well was attracting a plume, and that is why it went up so fast. Mm-hmm. That was hydraulic hypothesis. Yeah. Then the chemist had another hypothesis. He says the nitrate goes down, it is degraded, it is reduced because you have organic material in the soil. And then the bacteria, if there is no oxygen, they use the nitrate as the NO3 as an electron acceptor, and then they eat up this nitrate. The organic substance in the soil. Yeah. But now, if you do that for many years, the organic substance will be away, and then the filter will break through. So he had the breakthrough theory. Yeah. And then there was von der Pluch. And von der Pluch said, well, let's look at the use of this land. And he said, well, there were meadows, and then after the war, they would turn all these meadows into agriculture to produce more food. And then if you plow a meadow, it has a lot of nitrate in it. When it is mineralized, you get a whole plume. So these were the three hypotheses. Yeah. And now you bet who was right. Who was right? It was the soil scientists in the end. Yeah. The soil scientists combined with this shift, of course, that the plume was pulled to the wells. And the chemistry was not that important yet. So you see, that was the intellectually interesting thing. Yeah. The frustrating thing is that you could not do anything against it, even up to now. The problem is there. I think we have done some progress. We paid farmers for not fertilizing or having some meadows without fertilizations in the catchment of a well, but you can do that only in catchments. That is why it was so important to know where is the catchment so that you spend the money in the right place, right? So that, I think, helped, but in the general wide area, up to now, it is not a solved problem. And I think it cannot be solved if you want to have a highly yielding agriculture. Yeah. It doesn't work without fertilizers. Sure, no, and even I did another project when I was already in Kassel, where we looked at the organic farming. Now there you don't put in the artificial fertilizer, but you do this succession of different crops, rotation, and then you grow the nitrate-fixing legumes. And then the nitrate is in the soil, and then you come with your other crops in the next years. But that means you load that soil with a lot of nitrate, and it is easily washed out.
Yeah.
So it was for the nitrate in the groundwater not really a solution.
Yeah.
So these things you see, that was the experience I gained. Intellectually very good, excellent. You could also find some nice modeling of these processes, which I did then in Kassel, but no solution. So that's not for engineer, it's not very satisfactory.
Yes, so that was a bit of frustration, right, in that type of research or projects that
Yes.
you cannot really find or achieve the solution. But career-wise, during those years, you developed a lot of groundwater modeling tools, and you became a big name, I would say, in groundwater modeling. Flow and transport, like you described already. You also wrote some computer programs. I remember even the book Groundwater Models in Basic.
With samples in Basic, yeah.
In Basics, yes. Which was a very nice book to learn the groundwater modeling. And also later the Aquifer Simulation Model, ASM. And I remember I once got a copy from you, the conference. And then later processing ModFlow. So a lot of software development that you have been also supporting or helping to establish. Can you tell a little bit more about that all?
Yes. Yeah. Well, I think it was part of the teaching, because I thought you cannot teach modeling without hands-on experience. So you need something, and I did it in class even, that everybody had a computer, and we did this modeling together. So once you have this experience, you can learn virtually, and in the sense that I finish a model, and then I ask the question, what happens when? And this is where I think really the advantage of modeling comes about. In seconds, you can change a well, you can change a boundary condition, you can change the recharge, and you see what will happen. So you get a feeling for what would be important to look at in the field. I never separated the experience in the model with experience in the field. For example, I forbade my students to make a model of a place which they have never been to, even if you're on the surface. Yeah. The picture which you make in your mind, not having been there, is very different from what you make, the picture you make when you have been there. Yeah. I've been very lucky to know a number of hydrogeologists, field hydrogeologists, who have a picture of that vessel. Yeah. What does it look like? And if you don't have this kind of picture, you cannot make a good model. Yeah. This conceptual thing is quite important. Mm. But then, of course, all the numerics, etc., we improved numerics. I did also some more mathematically minded work. Yeah. And we used also these models for this subject of catchment areas, protection perimeters. It was a very satisfactory kind of work. We also used these models for remediation schemes. We did a lot of work for the lignite mining near Cologne. Yeah. This was a government agency who had to check whether they should allow or not allow for this brown coal, this lignite being exploited. And we did the modeling, and it was during that time that I had a student helper who was not able to copy, because everything had to be entered in the computer in those days by hand, to copy figures correctly. So I said, we cannot go like that. I must see the errors he makes. We have to show these data graphically, and that is why we developed the preprocessor for ModFlow. Yeah. Because it's a preprocessor, you immediately see if there is an outlier or some hole or something in the data. So that was the motivation to have this. But also, like in the predecessor, this ASM model, which was done for the teaching, and which has been used a lot all over the world, because we gave it out for free. Yeah. And one of the reasons going to ModFlow was we can go in 3D. ASM was just for learning in 2D, and we went to 3D. And you have to check your data. And there is only one way, that is to have this interface that you can look graphically at what you have entered. And also to look at the results is of course something where it has to look at one point. Doesn't make much sense unless it is the well, where you want to know a concentration of the well, but you want to see the whole thing, and that also needs some post-processing. So they made this pre- and post-processing for Botflow, which is a model everybody has. So we made something which everybody who uses that model can use for their own modeling. Yeah, I think it was also a very successful thing, which people were grateful for. I taught courses with it. I think I taught a lot of people. If you look at the people in Germany under the age or above the age of 40 who have been doing or do groundwater modeling, most of them would know me, or I have been at a course of mine.
I can imagine, yes. No, the processing Modflow was very influential, I think, also as a initial interface for Modflow. Yes. No, excellent. But also in those years you developed further strong overseas collaborations. And can you give a bit some examples of where else in the world you spread your wings, and what motivated you to do those overseas projects?
You know my love for traveling in the world, to China and to Nigeria, and I didn't lose that love for seeing something of the world, and still China and Africa were my biggest interests, because I had my good experiences there and I loved the places. So where else did I go? Well, during the time in Heidelberg, I started my cooperation in Botswana. That is one of the nicest experiences in my world, to work in my life, to work in Botswana. It started in a strange way. It was also because of a course. Well, somebody called me, still in Kassel, whether I would come to South Africa. I said, I don't want to go to an apartheid state where my wife is not worth as much as I. That's impossible for me if you have this state policy. And then this guy, Gerrit von Tonder, by the way, he said, but if apartheid falls, would you then come? I would say yes, then I would not have a reason not to come. So after that phone call, I was already in Heidelberg. 1 year later, he called, apartheid has fallen, will you come? I came. So I went there to give a groundwater course in Bloemfontein. And I was disappointed. Not by the course, I gave the course as usual, it was very nice and people like it, but there were only 3 black faces. And 2 of them were Indians, and 1 was a black guy from Botswana, that is Comfort Monosila. And this guy, he had a consulting firm in those days in Botswana. And we talked about it. He said, can you sometimes help us? So I said, well, we could help you with modeling and support you in this thing. But let's make a deal. I also sent some students to do some practical work with you in the field. And you can send people to me to learn something or do some work on your consulting business. And you will host them, I will host your guys. So we don't have to change these currencies, German mark into Botswana pula. We just have a stake against a stake. Right? So he said, let's do that. And that turned out to be very successful. I really liked my students to go to Botswana. Number one, even in Switzerland, we continue that. In Switzerland, everything works. So students don't have to develop the art of improvisation. But in Africa, nothing works. So you have to improvise. In the end, it works. That is my experience. That is a marvelous, marvelous thing. But you have to improvise. And that is what they learned. And also, I think they learned to have more respect for the local people. Why? Once you go with your African counterpart into the bush, he knows how to move and you don't know it. And then you get something called respect. So that is a nice experience, I thought, for my students. One of my students who went there was Philip Muller. He did a lot of work in Botswana, very interesting work. So
and also Peter Bauer.
Yeah, then that is the next step. The next step was that during my work there, because we also had contact with the Department of Water Affairs, one day the permanent secretary asked me to visit him. It was Professor Tambale. And he said, look at this, and he had 10 volumes. They want to take water from the Okavango. We have the WWF who does their business. We have the industry and Namibia who wants to take the water. They have their business. We need some neutral research of what we should do, whether we should be against it or for it. Mm-hmm. So can we set up a program? And we set up a program along the same lines. I had people who went to Switzerland for training, and then we went there and we had all the boats you need in the delta, etc. And this was one of the nicest projects in my life. And this was done by Peter Bauer, fantastic work. He's now a professor in Denmark. And and one of the scientifically nice things which came out of it is this observation of how the delta manages to stay fresh. Mm-hmm. I mean, you think if something flows into a region and then it all evaporates, then the salt will be left over and no time it will be a salt lake. Yeah. No. Mm-hmm. And the way this delta is keeping itself clean is by having some waste deposits. And these are the islands. The trees are pumps, they evaporate, and then the water below the island becomes more and more salty because the salt does not evaporate, it's only the water. Yeah. And then if it becomes really salty, then it's heavier than the fresh water around it. It drops down to the deeper aquifer, which is saline. Yeah. So that is the way how the delta keeps itself clean. Yeah. And even in Lake Chad, which I had been to much earlier in my career and came back to much later in my career, it's also this kind of mechanism which is seen in branches of the lake where the land stores the salt and pushes it down to a deeper aquifer. So that's a marvelous thing. Yeah. But it also meant that you have to, in the management of the delta, you must maintain the dynamics. Because the island, of course, it will die off after a while, and then you have a new island which can take over. So you need the dynamics. You cannot limit the amount of water which comes in because you need it for this delta to go left and right in time and renewing something while depositing the salt in the other part. And so that was our kind of applied thing that we said to Professor Tambale, don't do that. Don't agree to that plan. Yeah. Because they wrote, we only take out 1% of the water in the year. Yeah. But then if you look at the change, rainy season when the flood comes, and then the dry season, in the dry season it was 20%. Yeah. So this averaging in hydrology is a very terrible thing. Yeah. And so we told him, don't accept it. So they opposed it, and I think we did something good for the delta. Yeah. Whether this remains like that is the question, because the Angola is developing in the upstream, so we will see what happens.
Yeah, a lot of water comes from there, right? Mm. Yeah. And so that was a very exciting environment, hydrologically very dynamic. But back home, you moved again, and this time from Germany to Switzerland, to the ETH. And that's where you have spent the last 18 years of your career, and your random walk went into a number of other research fields, especially agriculture versus water, but also turbulence you worked on with quite some people. What value gave ETH to this last big part of your career, and what again were some of your highlights?
Now, let me just say one word about Heidelberg.
Okay.
In my 3 years in Heidelberg, I still learned a lot about tracers, because that institute was specializing in
isotopes,
isotopic tracers, C14 and all these things. Yeah. And I had good cooperation with colleagues around that institute. We did, for example, column experiments with heterogeneous columns using paramagnetic salts as a tracer, and then looking at it in an NMR picture. How does the water flow in this obstacle course over there? So using NMR was one thing which I later also used in Zürich. And I did also one thing together with a professor in physical chemistry, that is developed a flow cytometer for particles, tracers, used as tracers in groundwater, fluorescent particles.
Yeah.
So a particle tracer was for me interesting. I mean, tracers are interesting in the sense that every tracer who goes through that medium tells a different story, because every tracer sees something else. So multi-tracer experiments was something I thought would increase our knowledge and also the basis for modeling. So that was Heidelberg, so it was very useful for me to be prepared. But as I was more interested in really doing something as an engineer and not just develop a scientific method, I followed the call to ETH. Yes.
Yeah. And so at ETH, can you tell us a bit more, let's say, about that? On the one hand, you did turbulence research, but also very different agriculture versus water, big global problems.
Very varied problems. I mean, the turbulence part, I inherited some equipment from my predecessor, and that was the equipment to do what is called PDV, particle tracking velocimetry. It is a way where you put particles in a flow and then you follow it with not 2 cameras but 4 cameras for increasing the redundancy, and then you follow each particle and you can reconstruct its path. So we get all these path spaghetti pictures which you can then interpret and learn something about turbulence. Yeah. So for me this was just, I saw it and I said I want to do that, because that was like maybe in the marble paper with my father. So we went into that, and I renewed all these machines we had, the cameras, faster cameras, etc., to get to higher resolution numbers. And I must say that is where I really experienced what a fantastic environment ETH is. Yeah. And the reason is that I had never published one paper on turbulence, right? Yeah. And I applied for the research money, and the school gave me that money. You know, they are very careful in choosing the professors, but once they're there, you get a lot of trust. So they trusted me that I would make something useful with that money. And then I had a group of PhD students and doctoral students, 4 or 5 of them, and they were playing ball with each other. They pushed each other up, and we did a lot of stuff which you can find later, but that would be the subject of another talk, not of groundwater, right? Yeah. But in groundwater we continued. I had a very good colleague, my deputy, Fritz Stauffer, who had the experience from the unsaturated zone and the multi-phase flow, and so we worked together, and I think we had the chance to do a lot of interesting things during that time. Yeah. Of course, this work in Botswana, that was also done mostly in Switzerland. Yeah. And I would say one other thing from my Zürich time, you mentioned agriculture, right? Mm-hmm. So agriculture and environment or groundwater, that is something which up to now is one of my real concerns, because it has to do with sustainability. Mm-hmm. It's very difficult to explain what is sustainability, but it's very easy to explain what is not sustainable. Not sustainable, a practice which, if you go on with it, it leads you into some disaster. And we have seen that with the overpumping of aquifers. We have seen it with the pollution, salinization of aquifers. And these are the 2 things which in arid regions are the main problem. That on one hand, because it's a very evaporative environment, just like the Okavango Delta, you increase the salinity. Mm-hmm. And on the other hand, if you use too much groundwater, it comes up and the water tables go down. Yeah. Now we did work in China on that, in 2 regions. First we did this sustainability study in Xinjiang, the most western province of China. And it's a place where farmers irrigate with surface water from reservoirs in the mountain. And if in a desert environment you irrigate, there is no way to prevent the rise of the groundwater table. And if it comes within a meter or 2 of the soil, then the capillary action starts to evaporate groundwater, and to leave the salt.
Yeah.
And then it leads to this salinization, which you have also in a lot in Australia.
More than
Actually, there is another story of my Australian experience. Before going to Xinjiang, I got money together with a colleague from MIT and a colleague from Tokyo University. This was an industrialist, Schmid-Heini in Switzerland, who gave money to ETH if they cooperate with these three on the subject of sustainability. So, then I found these two colleagues, and we were thinking, what is the main problem in groundwater? In water, where do you use water? And then we found, 60-70% of water on the earth are used for producing our food. And then where do we use groundwater to produce that food? And then Dennis McLaughlin wanted to go to Australia. That's the battlefield. Let's go to Australia. And then we found they irrigate the wine. I said, we cannot save the world by making it drunk. We have to do something with grain. So we found only 2 grain crops are really irrigated. That is the maize in South America and the maize in Southern Africa. But he said, I want to go to Australia. So we found that in the Murray-Darling Basin, you have rice, which is a joke to do rice in that area. And we also found that out in our research, and nothing came out of it. We did not publish anything for the money we got. But I learned everything about salinization which I needed, and then I could successfully start the work in Xinjiang, in China. So you always have to go through a learning process when you go in a different field. And this money by Schmid-Heini was our school money for learning how to do salinization. And then we could do that there. And I must say there is still a bad taste in my mouth about this project. Not politically, nothing. But it's a bad taste which is a bit similar to what the Hydrogeological Survey of Britain did in Bangladesh. They said, don't use the surface water, use the groundwater. And that started the biggest collective self-poisoning with arsenic in the world, right? So was that a good decision? Well, less people died from diarrhea, that's for sure, but more people got skin cancer. So how do you judge that? It's this unintended consequences. And I think we had the same problem in Xinjiang. In Xinjiang, we did a good job. We analyzed this, we modeled it, and we said, you have to pump groundwater to keep the groundwater table below that extinction depth, then you will not get this capillary rise. And we installed this groundwater pumping wells, etc. And the farmers loved it too much. Why? Well, it's so easy to do the water-saving agriculture with groundwater. You just switch it on, you put it through your drippers and this drip irrigation equipment, and you can switch it on and off, and small and large, whatever. If you want surface water, you have to telephone the dispatcher in the mountains. He will open the sluice gate. The water will come down after 1 week. A lot, you cannot use it all. How do you store it? And that was very inconvenient. So they loved this. But they loved it too much. Now, this place, as far as overpumping is concerned, is the number 1 in China, even more than the North China Plain, where I used to work for about, till 1921, for 6 or 7 years. And where we tried to curb this overpumping by several measures. So the North China Plain is now looking much better, not because of us, but because of the South-North water transfer, which helped a lot, and also replacing some of this winter wheat, which in the dry season uses most of the groundwater, by replacing it or by subsidizing people not to grow that. So these things helped, and I think it's on a good way now. It's not yet up, but it's either stabilizing or slowly going up. And we have, the St. Peter is also helping a bit by having given more rain over the last few years. And this is an interesting thing with climate change. They have more of these heavy events. And the heavy event is much better for groundwater recharge than this gradual distributed rain. I know this from South Africa, where one event will recharge the groundwater, and then no more recharge until 10 years later.
Yeah.
And so it goes down, the plants use it up, not so much the people, and then it comes up again. So this is something which I thought helped the place nowadays, so that North China Plain is no longer problem number one in groundwater in China.
Okay, and all of this agricultural water work for you, how do you see that? Because many people talk about a world water crisis and that food production needs most of the water. I think you have mentioned the value, 70% of all the water. And the overpumping that it is causing. India is a huge example, some of your Chinese areas. Would you have ever expected this to be a major issue when you started your career? Is there really a world water problem for you? What role do you see scientists like yourself or the future generation and academics playing in solutions?
This I would not say world water crisis. I would rather say world food crisis. Because a pumping of a farmer in Australia will not influence the pumping of a farmer in the United States. But if both don't have groundwater anymore, then both will not export to the world market, and then prices will shoot up. We had this price for pizza really going up because grain was more expensive for a certain time, where both meteorological events and this lack of groundwater, these things led to an increase in price. So this is something which I think can happen again and will happen again. Because as long as we do not adapt the productivity of a place to the available water, we will have this overpumping. And I think the only way is to have less intensive production. Now, who wants to do that? It's a big problem. In China, we suggested that limit the amount of fields and limit the amount of things which are grown. And then they say, but we need to produce to feed our people. We don't want to depend on all these imports from the US, from the enemy, of course. So you see, it becomes also a political problem of independence. So at the moment, I think it's very difficult to solve, but I'm not that pessimistic. Why? Because if you look at demography, China in end of the century will have about half of the people it has now. And with half of the people, I would think this water resources problem goes away. And for other places, we can be easily also more pessimistic. I always thought, when I was talking about this so-called world water crisis, we have to go over a hill, and afterwards the problem will go away. Of course, that hill, worldwide, we are not yet on the top, but for some countries like China, we are over the hill. It's going down. For India, we are just there, and it will start to go down. The only continent where a really population grows is still unfettered is Africa. So that's still a problem. And of course, I would say some of these political problems we have in the Middle East, they are in really a big problem with the lack of water.
Absolutely. All this work that you have done was very successful, and you had done lots of projects and research and papers written, and it has shaped your career, but behind it is a certain philosophy to life that you hold probably. And I would be interested to know a little bit more about that driving inner factor from you that helped to create your success, but maybe you also see some failures in your work, don't know, and how that generated your major milestones.
The philosophy. I told you about my decision in Stanford to go away from theoretical physics to something which is more relevant to society. That was a big wish, to do something which is useful for people. And also having seen on my travels poverty in the third world countries, I thought, can I do something? Like going to teach in Nigeria was something like that. Also to go to rural China, which also used to be poor and still is poor right now, to help to improve the situation. This is a wish, of course. The wish to develop a place. I tell you, I did not develop anything, but I developed myself. So please, I have to be very modest about that. These problems are so big that you don't solve them alone. But even the problems we solved, I must say, they were solved not only by me, they were solved together with all these PhD students and master students and postdocs who worked with me. So one has to be clear about that.
I will come back to that. And so in that whole work and the career, are there some outstanding fond memories that you have? And also, what did working with other colleagues or people meant for you? Have you made friends on the way in your career? Was it an easy way of traveling through your career, or did you find it difficult?
Yeah, when you talk about friends, I have a lot of friends, but they're all over the world. I asked my daughter, was it terrible for you to go also all these moves? I moved 11 times more in my life. And she said, it was good. The only difference she feels to people who stayed is that their friends are in the town or in the village, and her friends are distributed all over the world. So that is a price which you pay. Of course. But this satisfaction, I think I was always quite satisfied with the work I did with my students. And I think it was societally relevant. In some places we really added to a solution. I mean, when decisions are made, big decisions, then only in the case where it's almost equilibrium, your scientific thing will push it to one side. If the game is so much, then you can do as much science as you want, and they will spoil the earth. And this is what is really happening now. But sometimes you have this happy situation where your word helped to push the scales to that side. Right. Friends, of course, in science I found a lot of friends through cooperation, of course, not only in the African cases and in China, where I have a lot of friends, of course, but also very weird things. Once I was asked by the Department of Agriculture in the US to write a paper, but their format of the conference was that each subject was represented by 3 scientists from the US and 3 scientists with the view from outside of the US. So they asked me to write a paper, and they had the names of the people whom I have to cooperate. That was Peter Dillon from Australia, and Dennis McLaughlin from MIT, and myself. And we had to write about the impact of nitrate on groundwater or something. I don't even remember the subject anymore, influence of agriculture on groundwater. And I didn't know these 2 people, so I thought, that's weird. Why should I do that? So we contacted each other and said, well, it's so weird, the idea, to just throw us together by the dice, that we will do it. And we did it, and we got to know each other, we visited each other, and we became friends, even up to now. And writing to those guys, and I have contact with them, it's really nice. So you see, also on that side, you have a game in science.
That's one of the great benefits of being a researcher, that you get the opportunity to travel and work with so many different people in the world. You clearly did that. Now, if I go back again to your early start of your career, mid-1970s, I think research and universities were a very different place as nowadays. And the pressure to publish was probably much lower than today. I also know that you and your students have published a lot in German, language, but also in conference proceedings, which was, and I still remember that as well, quite normal and important to do. How has academia and research for you changed over the years, and how do you see it heading, for the good or for the bad? And what's your opinion?
Yeah, I mean, you should never ask an old person about this, because they would say earlier in time everything was better. But that has been told generation by generation, so now the earth or the world should be at the lowest point ever. That is rubbish. But still, I would say in those days it was really that when we had spoken about a result at a conference, we thought that is published and that was it, and then we went to the next subject. Nowadays, a conference proceeding is not considered as anything valuable. They print all these big volumes and nobody will ever look at them again. So that is why people said you have to publish in papers which are peer-reviewed and then a certain quality assurance. And then, so that came then gradually. I think a lot of my stuff is somewhere in this grey literature, which nowadays would be in a good journal. And is it good or is it bad? Yeah, I think it is good if the peer review system works well. It is good to have this choice and have these places to publish. But on the whole, I think it becomes so much worldwide now that you have no chance to look through all that literature. It also leads to the effect that many things are invented again and again. There's a lot of repetitive science, and how can we solve this information problem? That is for me a big thing. Maybe with artificial intelligence we'll squeeze out this real information from the stuff available from everywhere. But this what has changed, and which I don't like. Many things I'm open to change. I've always changed. I've reinvented myself as far as the subject of research goes every 3 or 4 years. But one thing which I changed is that nowadays we have to make much more propaganda for ourselves. You know, in earlier times there was kind of this societal agreement. Science is important. Give them their money. They do something, and the society can use it. Nowadays this is much more in doubt, and we have to prove every day how important we are to society, and that of course leads to this competition who has the bigger catastrophe, right? And also when you make propaganda in itself is already this thing, it's not completely truthful, right? And science is about truth. And if you mix it with this propaganda, I think we lose some of our purity in science. This is what I'm a bit concerned about.
No, I can imagine, And so in that sense, where do you see the future of groundwater hydrology heading? You said earlier, I think also that you were kind of at the start of a groundwater research area with all the pollution, contaminant, transport issues. So do you see, or what do you think will be some exciting areas for the future? Or I don't know, exciting areas anymore.
Was it really science? I was doing applied science. Of course, we found some basic things on the way here and there, but it was always applied science where the problem comes from the reality, from people. And so what about hydrogeology? Is there hydrogeology as a pure science? I think the learning curve of all this hydrology has become very gradual. If my daughter would ask me, should I study biochemistry or hydrogeology? I said, do you want to be a scientist or do you want to save the world? If you want to be a scientist, go into biochemistry. If you want to save the world, you can go into hydrogeology if you want. So this is the thing, it's applied, and we follow these projects. But the thing is that we can solve this old bloody problem with better and better tools. That is where we make progress. Let me give you an example. I had a project in Niger, and we needed the piezometric head of a certain well, which was 400 kilometers from Niamey, which is the capital of Niger. And to get one value every month, you have to go 800 kilometers to the bush and back, 12 times. Then the data logger came.
Yeah.
Then we put in a data logger, and we went twice a year
Yeah.
to milk it.
Yeah.
Of course, you had to go twice a year. The only thing which happened is that a flash of lightning went into that well.
Yeah.
That is the only danger. Though.
Yeah.
And then it came even better. Then we had the data logger with some connection to satellite, and we could look at the data at home.
Yeah.
So you see the same thing, but many more data. And this data, which goes like this, on high resolution, every hour or so, or even less, there is a fingerprint in it from which you see much more than from this monthly value. Let's say you miss one. How to connect 2 points? Does it go like this or does it go like that? You don't know. So this is where this continuous data then give you a story where you have much more knowledge. So this is a small example of which is already there. But I think we had in the last 20 years some things which have improved, or we got really new tools through science, through basic science, is the GRACE, for example, the gravitational field and its temporal change being associated with water, the water cycle. That helps a lot on the large scale, not on the small scale one. We have had the Cosmo probe, where with the neutron scattering you can measure with a large footprint, not only at one point, like in a tensiometer. You can measure the moisture of a soil over a larger footprint. This is some real new thing which you have. Krypton 81, we have now a dating tool which is in between the very long C14 and the short ones which are tritium or something. So these are new things which came as tools and make our life better. Of course, I will also say remote sensing. Remote sensing, we also wrote papers of how to use it in groundwater, and there is a lot of chance you have. Yeah. It's not that you see directly the things you want. But there is a connection, there is a correlation of what you see.
A proxy.
It's a proxy, be it in the visual, be it in the radar. We use also a lot of radar stuff now. Yeah. There is it's a proxy, and via a model you can connect it. Maybe sometimes not so much the value of that proxy, but the pattern. We did groundwater model calibration with pattern information. Patterns, right? Normally we think we make zones. If you have a lot of zones, you want to have one value in each pixel of your grid. It's hopeless. You can never get a unique interpretation or a unique fit for that. Solution. It's always many possible fits. It's not unique. Yeah. Now with this pattern, you shrink the number of possibilities a lot. And I said hydrogeology is the old science. One thing where you see a scientist getting old is that when they start to do things stochastically, because they hit into the wall of how much you can deterministically really see. Okay. And that has been done in hydrology, and it's now done in hydrogeology, that we have to become stochastic. So we don't have these very strong statements anymore. We have the statement, it can be between this and this, or this is the more probable scenario, this is the less probable.
Maybe more realistic answer. Huh?
Well, more humble and more true.
You did, of course, also teaching, and you worked with students and you supervised students. What did the teaching and the supervision mean for you? Was it has it been rewarding to do that, teaching and supervision? And what lessons? How did it teach you as a teacher or as a lecturer? And how have you combined always your research and teaching? Was it a struggle or was it a pleasure?
No, I really always loved teaching. Yeah, I love to talk, as you know. But what I miss most after being in retirement is this contact with my young students and PhD students, master students, etc. In a sense, what did I get from them? I get this freshness of ideas, the challenge, this to and fro, And sometimes I felt like a vampire who is sucking the blood of youth to stay young. Yeah, I had a lot of my students, I must say, and I had very good students. I have quite a number of students who have become professors now.
No, you had a large influence on the community via your students, that's clear, yeah. And in all that work that you have done, and you mentioned some of it in the beginning of your career, you got support from colleagues, but maybe also family and friends.
Of course.
And what has that meant for you? And also family and friends, and I'm thinking about what a lot of people struggle with in terms of work-life balance. How did you manage that?
Let's say friends. I had friends, I had people who supported me, who, like coming to ETH, for example. I think it is due to Professor Stumm. He was the head of ERWAG, Stumm and Morgan, very famous geochemistry book. And he was the one who asked me, would you come? You don't even have to apply, we call you. And that's how it worked. He really liked the kind of work we did, and we had a kind of a common understanding. We taught a course together sometime. So he was this kind of thing which a young scientist needs, a mentor who helps you, who is there for you, without thinking about what can I gain out of it. You know, this is the thing. You have to be unselfish, and that is what I try to do for my own students as far as it was in my capability. So friends, this work-life balance. I like this stuff so much that I did not see a contradiction between life and work. It was like a paid hobby for me, right? Maybe where I made a mistake is that I took my career over the family. So the students had to follow through these countries, and I was moving up in the career ladder. So maybe that was a bad part of it. Another bad part is I'm quite critical, and I'm very fast in finding the fly in the soup. And maybe I should have dealt out more praise than criticism to my students and my children.
Okay. No, that's an honest evaluation. And so you said already you have tried to support your students also as you were supported. I suppose you also it's quite clear that you have given a lot back to the community, research community, the society, in terms of all your practical projects. Does that mean that you hope to be remembered, let's say like that, in a certain way when people reflect on your future?
No, I couldn't care less. When I'm dead, I'm dead. I don't care. What I care about is that people respect me and like me now, as long as I'm still alive. Maybe there's a small thing. I tell you a small thing. You know, all these famous people, they have a number. There's the Fruit number, and there's a Reynolds number, and there's such and such number. And I say I have a Kinzelbach number. You know, and I have a candidate. We did some work on these catchments in when I was still in Kassel. From Marburg, we did, with this thesis, we did this development. And you know, what does the catchment of a well look like in 3D? Well, sometimes it is like this, that it's just like a oval, but many times it goes back to the boundary. It's stretched long, or it's like this. When is it like what? And we found a number, it's called kappa, so already for K, Kinzelbach, you know. Kappa, a dimensionless number where you put in distance to the boundary, rain, recharge, popping rate, etc. And then you get a number which tells you when you get this long 2D type or the small 3D type catcher. So if that would be called Kinzelbach, okay, you have to do something for me.
Yes. Okay, we'll talk about that later. How I can
I
help
don't even know whether I still have a copy of that paper.
Yeah, okay. Fantastic, yeah. We'll have to promote that Kinzelbach number. Yeah. Wolfgang, we're coming slowly towards the end, and I'd like to ask you at least one more question here. And you're known for outspoken opinions, let's call it like that. And you just mentioned yourself that you can be very critical, and which has certainly its good side in science. And I hope, therefore, that we still can get out of you some final message or words of wisdom for the current and the future scientists. If you want to, what would you like to give them along as a message? Or is there? Do you say I don't have any message for?
It's not an easy question. Of course, you know, I'm not a diplomat. I would not be qualified to become a diplomat. That's for sure.
Okay.
But maybe one thing, you know, many people they do science and just run with the bandwagon. Now everybody's doing AI.
Yeah.
I think it's such a waste. Everybody goes to AI. You should do things where you, in your heart, are convinced of, even if it is growing somewhere in the shadow. Someday this will become important. You never know in science what will become important. You know, this is this wrong belief which all these science foundations, founding agencies have. They think they can plan where science goes.
Yeah.
Rubbish. Yeah. The science always came out from another, the breakthroughs, they came up from some other place. You cannot plan that. You can plan it in engineering. You can plan to go to the moon. Yeah. That is a step where everything, every element is there. Maybe a few you have to develop further, but it is a different thing from finding a relativity theory. That's very different. Mm-hmm. Yeah. So that is why I think this GRACE or the Cosmo probe, these are things where people did something, nobody knew about it, and suddenly it's there, and then it makes a big impact. Yeah. So one has to follow the heart. I know this about my students. Look at Peter Bauer. I mean, he was married to the Okavango Delta. That thing was really fulfilling him with enthusiasm. And that is how you should do work, and not just run after some other people because they have some new buzzwords. You know, they don't say model nowadays, they say digital twin. What a rubbish. It's the model, right?
Yes, yeah. Indeed. Okay, good. Thank you very much for those wisdom and words for the next generation. And thank you very much for doing this interview. It was great to talk to you and hear your fascinating stories of your career. And thank you for your contributions and inspiring contributions for groundwater, actually much more than groundwater. You started in more surface water and water temperature. And I wish you and your family all the best.
Thank you very much.
Yeah. Thank you. Okay.